You sit down at your desk, you place your hands on the keyboard, and you expect this completely seamless, frictionless translation of your thoughts right onto the screen.
Right, yeah, like it's magic.
Exactly. I mean, you need a curly bracket to write a block of code, so, you press the curly bracket key, you need a hashtag, you press shift, and the number 3. It's a completely one-to-one relationship.
It really is. I mean, you press a physical button, the symbol appears, and the computer just understands it perfectly.
Yeah, and it feels like a fundamental law of physics at this point, right?
Yeah.
Here in the 21st century, we take the sheer, I guess, real estate of a modern keyboard completely for granted.
Oh, totally. We absolutely do.
But today, we are pulling from this fascinating historical deep dive. It's this dense, highly detailed Wikipedia article on the history of digraphs and trigraphs in programming.
Such a good topic.
Right. And our mission today is to uncover how a severe lack of physical, plastic keys back in the 1970s and 80s created these bizarre, invisible software ghosts.
Ghosts that are, frankly, still haunting modern code bases today.
Yes, exactly.
Yeah.
So we're looking at what happens when the computer language you're writing in literally demands a specific symbol like, say, a square bracket or a backslash that just physically does not exist on the keyboard sitting right in front of you.
Yeah, it's essentially like trying to play a complex classical piano concerto on like a child's toy keyboard.
Oh, that's a great way to put it.
Right. You physically do not have the keys to hit the notes the sheet music requires. So to keep the music playing, programmers had to, they had to invent these complex, unnatural chord combinations just to hit a single missing note.
Just to get by.
Exactly. And the really wild part here, the thing that's so fascinating, is how those desperate temporary bandages applied to early hardware limitations permanently baked themselves into the infrastructure of our whole digital world.
It's wild. Okay, so let's start by defining our terms for anyone who hasn't, spent time digging through the dusty archives of computer science.
Good idea.
Digraphs and trigraphs are essentially just sequences of 2 or 3 characters in your source code that the programming language is explicitly instructed to treat as a single, entirely different character.
Right.
Like you type 3 things, but the computer pretends you only typed 1.
Which sounds horribly inefficient, right?
Totally. Sounds like a nightmare.
But early programmers simply didn't have the luxury of choice. I mean, today we have Unicode, which is this massive, universally agreed-upon library of characters. Every computer on Earth understands it.
Right. It's just standard now.
Exactly. But in the early days of computing, hardware was wildly fragmented. You had systems running on something called EBCDIC.
EBCDIC.
Bless you. Yeah, right. It stands for Extended Binary Coded Decimal Interchange Code. It was this old, proprietary IBM character encoding standard that was primarily used on their massive mainframes.
Okay.
And EBCDIC code pages were notoriously limited. Depending on the specific version running on your machine, standard programming symbols like curly brackets or square brackets, they simply did not exist in the computer's brain.
Wow. I have to imagine that writing modern code without a curly bracket is like, I don't know, trying to build a house without nails. It's just a structural impossibility.
It fundamentally breaks the syntax of most languages. And, if we look even earlier at a language like ALGOL, developers were dealing with manufacturer-specific 6-bit character codes.
6 bits?
Yeah, 6 bits, which only gives you 64 possible characters total.
Oh, wow. That is nothing.
Right. Once you account for uppercase letters, numbers, and basic punctuation, you are completely out of room. They physically lacked the code points for the mathematical operations the language required.
So what do they do?
Well, they invented substitutions. So to assign a value, which conventionally looked like a left-pointing arrow in their documentation, they had to type a colon followed by an equal sign.
Okay.
And to write, say, greater than or equal to, they typed the greater than bracket followed by an equal sign.
Okay, let's unpack this because that actually makes perfect sense when you think about like early smartphone texting. Right. Before we all had dedicated emoji keyboards natively built into our phones, if you wanted to send a smiley face to a friend, you had to physically type out a colon, a hyphen, and a closing parenthesis.
Exactly.
You were combining existing, unrelated characters to represent a visual concept you just didn't have a single dedicated key for.
That is the exact same psychological workaround, just applied to the structural architecture of software.
Wow.
But, with texting, a human reads the colon in parenthesis and interprets the emotion. In early programming, the computer compiler physically translates those characters into a functional piece of the program itself.
Right. It actually changes the code.
It does. And where this mechanism gets incredibly complicated and historically chaotic, really, is when we look at how the C programming language handled this whole hardware crisis.
Ah, yes. The infamous C trigraphs.
The ones and only.
Looking at the source material, the basic character set of C heavily relies on ASCII, which is a 7-bit character set. But C, specifically, requires 9 distinct characters that sit outside the widely compatible, standardized subset known as the ISO 646 invariant character set.
Yeah, and we should probably clarify what that invariant set actually is.
You do.
ISO 646 invariant is basically the core, universally agreed upon alphabet, numbers, and basic punctuation that literally every computer terminal in the world could understand, regardless of nationality.
Okay. But the C language needed characters like the hashtag, the backslash, the caret, the vertical bar, the tilde, and both sets of square and curly brackets.
Exactly.
And those 9 characters were not in that universal invariant set. So if you were a programmer in, say, France or Germany, your national keyboard layout likely replaced those specific keys with local alphabetic characters.
Right, like letters with louts or accents.
So you physically could not type standard C code.
You couldn't.
Yeah.
So the ANSIC committee was staring down this massive international adoption problem. Their mandate was to ensure international programmers could type C code on absolutely any keyboard in the world. Their solution was the trigraph. They invented 9 specific 3-character sequences to act as stand-ins for those missing symbols. And the defining feature of these sequences was that every single one of them started with 2 question marks.
Okay, wait. I really have to push back on the logic of that decision.
Oh, I know.
Why use 2 question marks as your trigger? I mean, what if I'm a programmer writing a standard error message, and I genuinely just want to type a bunch of question marks in my code?
Like for emphasis.
Exactly. Like printing the text, critical error, what just happened? Doesn't that cause absolute chaos in the system?
Oh, chaos is putting it mildly. It caused catastrophic code-destroying bugs.
I knew it!
Yeah, and to understand the mechanics of why it was so destructive, we have to look at how the C compiler actually processes these trigraphs.
Okay, lay it on me.
So the compiler doesn't look at the context of your code. It doesn't know if you are writing a mathematical formula or just leaving a text note for a coworker. The tool responsible for these substitutions is called the C preprocessor.
The preprocessor.
Right. And it is designed to be a completely blind, brute force search and replace mechanism. It runs before anything else happens in the compilation process. It is the absolute first pass over the text.
Wait, so it's essentially just doing a mindless find and replace across the entire document before the actual brain of the compiler even turns on.
Precisely. It is totally blind to context.
That sounds dangerous.
It was. Let's walk through the specific, deeply frustrating example highlighted in our sources.
Okay.
Imagine a programmer writes a simple, harmless comment in their code. In C, you use a double slash to tell the compiler, hey, ignore everything else on this line, it's just a note for human eyes.
Right, standard commenting.
So the programmer writes their double slash, followed by the phrase, will the next line be executed? And then they add 10 question marks for emphasis.
Because they're very stressed about this line of code.
Exactly. 10 question marks, followed immediately by a forward slash, just as a visual divider.
Okay, so logically, since it is hidden behind that double slash comment marker, the compiler should just breeze right past it. It shouldn't affect the actual software at all.
That is the logical assumption. But remember the mechanics of the preprocessor.
Right, the blind finding replace.
Exactly. It runs first. It does not know what a comment is. It simply scans that line of text, and at the very end of the string of question marks, it spots a sequence. Question mark, forward slash.
Uh-oh.
Yep. In the ANSIC standard, that specific 3-character sequence is the official trigraph for a single backslash.
Oh, I see where this is going, and it is horrifying.
It really is. The preprocessor silently, invisibly changes those 3 characters into a backslash. Now, in the C language, placing a backslash at the very end of a line is a structural command.
What does it do?
It is the line splicing character. It explicitly tells the compiler, take the entire next line of code below this one and pull it up to join the current line.
No. Which means, wait, the actual functional line of code immediately below that harmless text comment gets sucked up into the comment block itself.
Yep, it gets completely hidden from the compiler.
Wow. The program will compile perfectly, but a crucial piece of logic is just magically gone because someone was a little too enthusiastic with their punctuation.
Exactly. It was an absolute nightmare to debug. I mean, you would stare at a screen of perfectly valid, structurally sound code, completely unaware that the preprocessor was secretly rewriting the foundational text behind your back.
Before the compiler even got a chance to evaluate it.
Exactly. And the source notes that developers working on the classic Mac OS suffered immensely from this.
Oh, really? How come?
Well, they frequently used a 4-character constant to denote unknown file types or creator codes. The constant was literally just 4 single quotes repping 4 question marks.
Oh, no. So every time they typed that out, the preprocessor would see those consecutive question marks, assume it was the start of a trigraph, and just mangle the code.
Completely mangle it. You would have to use incredibly convoluted string concatenation or weird escape sequences just to hide basic punctuation from your own compiler.
It seems like an incredibly blunt, almost reckless substitution method.
It was. And the sheer volume of these destroyed code bases forced the C Standards Committee into a corner. They couldn't just abandon the workarounds because, those international keyboards still lacked the physical keys.
Right. The French and German developers still needed to type.
Exactly. But they had to stop the preprocessor from blindly eating comments and strings. So their compromise, introduced in the 1994 C95 amendment, was the digraph.
Okay, the digraphs. So
Yeah.
they shifted from 3-character sequences, starting with question marks, to 2-character sequences.
Right.
For example, using a less than sign and a percent sign to represent a left curly bracket, or a less than sign and a colon to represent a left square bracket.
Yeah.
But wait, simply making the sequence shorter doesn't solve the brute force replacement problem, does it? It's still a blind find and replace.
Well, making it shorter wasn't the fix. The brilliance of the digraph was changing when the sequence was processed by the system.
Oh, okay.
Unlike trigraphs, which were aggressively replaced in that chaotic first preprocessor pass, digraphs are handled much later in the compilation pipeline.
During a phase called tokenization, right?
Exactly. Tokenization.
Let's unpack the mechanics of tokenization for anyone listening who doesn't spend their weekends writing custom compilers. How does moving the substitution to this specific phase save the code base?
Okay, think of tokenization like reading a sentence.
Okay.
If a preprocessor is told to replace the letters THE, it will blindly rip those letters out of the word there or theater and just ruin the sentence.
Because it's just looking for the letters, not the meaning.
Right. Tokenization, however, is the phase where the compiler groups individual characters into meaningful words or tokens. It actually understands context.
Ah, I get it.
It knows the difference between a functional keyword, a mathematical operator, and a literal string of text meant to be printed on the screen.
So because digraphs are processed during tokenization, they respect the boundaries of the code.
Exactly. If the compiler is reading a quoted string and sees the digraph for a curly bracket inside those quotes, it knows it is currently inside a text token. It leaves those characters alone.
Wow. It finally adds a layer of intelligence to the substitution. It solves the string and comment formatting bugs that made trigraphs so universally hated.
It really was a massive leap forward in stability, but, because this is the history of programming, layering new logic on top of old compromises rarely results in a perfectly clean system.
Of course not. That would be too easy.
Right. So when C++ inherited all of these digraphs, they ran into a fascinating edge case that threatened to break the entire language.
Yes. Here's where it gets really interesting. The source material highlights the less than : dilemma.
Oh, yeah. This is a great one.
In C++E, there is a very common sequence where a less than sign is followed immediately by 2 colons. Now, a less than sign followed by a single colon is the official digraph for a left square bracket. So if we follow the standard predictable tokenization rules, less than colon should automatically be interpreted by the compiler as a square bracket followed by a colon.
Which would be the expected logical outcome of the rule they literally just wrote.
But the C++ Standards Committee had to explicitly write a hyperspecific exception to stop that from happening.
They did.
They mandated that in this exact scenario, the less than sign must be treated as its own entirely separate token, and the 2 colons are left alone.
Because if they didn't, it would be disastrous.
Why? What would happen?
Well, the reason is that if they allowed the digraph substitution to happen, it would completely destroy the syntax for C++ templates.
Oh, wow.
Yeah, templates are a major feature of the language, and they rely heavily on less than signs and colons to function. So it is the ultimate architectural balancing act.
You are constantly patching the holes left by missing physical keys while desperately trying not to break the entirely new advanced language features you're currently inventing.
Exactly. It's a house of cards built on a foundation of hardware compromises.
But the funny thing is, while the C and C++ communities viewed these sequences as like a necessary evil, a frustrating bandage they couldn't wait to peel off, other programming communities looked at digraphs and saw an entirely new toolkit.
Oh, absolutely. They stopped treating them as workarounds and started using them as intentional features to expand what a standard keyboard was capable of.
The evolution of the Pascal programming language is a perfect example of this, isn't it?
It is. Pascal needed curly brackets for comments, and for keyboards that lacked them, they introduced the digraph of a left parenthesis followed by an asterisk to represent the left curly bracket.
Okay.
But the developers using Pascal actually preferred the workaround to the real thing,
Wait, really? Why prefer typing two keys when you could just type one?
because it offered a visual and functional distinction. A comment block that starts with a parenthesis and an asterisk absolutely cannot be accidentally closed by a stray, regular, right curly bracket floating somewhere in the code.
Oh, that makes so much sense.
Right. It provided a robust, distinct way to manage large blocks of comments, especially if those comments contained actual code snippets that used curly brackets. It was so popular it became a standard alternative.
Wow. And then the J programming language took that concept and pushed it even further.
J is wild.
It really is. J is a descendant of the APL programming language. And APL is infamous in computer science for using a vast, terrifying array of specialized, highly mathematical symbols that absolutely do not exist on a normal keyboard.
Yeah, symbols you'd expect to see on like a advanced physics chalkboard.
Exactly. When developers built J, they wanted to replicate that massive mathematical power, but they strictly limited the language's alphabet to the basic ASCII character set.
Which is a huge constraint.
So to pull off that illusion, J utilizes the period and the colon as what they call inflection points. They took the concept of the digraph and made it the foundational grammar of the entire language.
Yeah, let's clarify how those inflection points actually operate, because it's brilliant. It's essentially like adding a modifier key like a shift or an alt key, but doing it entirely through software syntax instead of physical hardware.
Exactly the right way to think about it.
In J, if you type a standard plus sign, it performs basic addition. But if you type a plus sign immediately followed by a period, the language treats that digraph as an entirely different logical operator.
Like a logical OR.
Right. And type a plus sign followed by a colon, and it becomes a logical N or R. By simply appending one of two standard punctuation marks to any normal character, J exponentially expanded its vocabulary without requiring a single new physical key on the board.
That is so clever. And we see this exact same philosophy, expanding a limited physical interface through sequence mapping pop-up in early portable hardware as well. The Hewlett-Packard RPL calculators are a prime example.
Oh, those HP calculators are fascinating. They were designed for advanced engineering, so they supported a massive extended character set internally.
But obviously, the physical keyboard on a handheld calculator is incredibly tiny.
Right, you simply cannot fit hundreds of keys on it. So HP implemented something called TIO codes. You would type a backslash, followed by two characters that visually resembled the missing glyph you wanted to display.
And if the symbol you needed was too abstract to draw with two letters, you could type a backslash, followed by a 3-digit decimal code.
Which is technically a tetragraph.
A tetragraph.
Also,
A 4-character sequence mapping directly to a specific memory address for a symbol.
the ingenuity of these power user shortcuts is just astounding, and you see it everywhere in classic software. Like the Vim text editor uses Control-K to allow users to input thousands of special characters via two-letter digraphs.
Right.
Lotus 123 for MS-DOS utilized Alt F1 as a compose key to build symbols out of sequential keystrokes.
So what does this all mean? What began as a desperate workaround for the physical limitations of a 6-bit mainframe organically morphed into a highly efficient workflow for developers across entirely different operating systems.
Exactly. The constraints of the physical environment forced a structural innovation, and then the users weaponized that innovation for their own speed and efficiency.
But as we know, the technological environment never stays stagnant for long.
Never.
If these digraphs and trigraphs were so deeply woven into the fabric of early compilers, operating systems, and developer workflows, why don't modern programmers ever see them today? What finally killed the trigraph?
Well, the trigraph was entirely eradicated by the widespread adoption of Unicode and the UTF-8 encoding standard.
Of course.
For decades, the tech industry suffered through fragmented code pages and regional keyboard quirks. But eventually, the industry rallied around a single, universal standard for character encoding. Unicode was designed to handle virtually every symbol, letter, and emoji in human existence.
So the digital map finally grew large enough to perfectly cover the entire physical territory.
Precisely. Modern operating systems became capable of seamlessly mapping any physical key combination to any Unicode character. The hardware caught up, and once that happened, the trigraph wasn't just obsolete, it reverted to being actively dangerous. Because of those blind preprocessor bugs we discussed earlier, having trigraphs enabled in a modern compiler was a massive liability for any codebase.
They went from being a lifeline to a landmine.
That's a great way to put it. They became so universally detested that compiler manufacturers actively started disabling them by default. If a programmer accidentally used a trigraph sequence, modern compilers would halt and throw a warning.
Oh, wow.
The company Borland even took the extraordinary step of ripping the trigraph processing logic out of their main compiler entirely.
Wait, really? What did they do with it?
They physically segregated it into a totally separate, standalone, executable program called trigraph.exe.
They literally quarantined the feature.
They did. Borland realized that forcing their compiler to scan every single line of code for a double question mark significantly slowed down the compilation process for normal code.
Which makes sense.
Right. Why penalize the vast majority of your users with slower compile times for a feature that almost no one used anymore? If you truly desperately needed to process trigraphs, you were forced to run your code through that separate quarantine application first.
That is an incredible logistical middle finger to a piece of legacy syntax.
It really is.
And eventually, the standards committees followed suit. Trigraphs were officially and permanently removed from the C language standard as of C23.
Finally.
But looking at the source material, there's one detail that stands out as deeply counterintuitive. Throughout this long, slow death of the trigraph, one massive tech giant fought aggressively to keep them alive.
Oh, this is the best part.
When the C++ committee proposed deprecating trigraphs in C++11, IBM stepped in and strongly opposed the removal. And they actually succeeded, at least temporarily.
The IBM holdout. It is a perfect illustration of how heavy the anchor of legacy code really is.
But why? Why would a modern tech giant defend a universally hated, bug-ridden feature?
The answer is always backwards compatibility. IBM, perhaps more than any other corporation on Earth, maintains massive, ancient enterprise systems.
Oh, right. We are talking about the mainframes that run global banking, airline ticketing, and international logistics.
Exactly. Systems that were written decades ago, heavily utilizing those very same limited EBCDIC character sets that necessitated trigraphs in the first place. For IBM, removing trigraph support from the modern C++ standard meant that millions of lines of foundational, mission-critical code might suddenly fail to compile when they updated their system.
That would be disaster.
Right. The risk of breaking a global banking system simply because you wanted to clean up some ugly syntax was unacceptable to them.
They were completely chained to the workaround. The ghost in the machine was holding the modern infrastructure hostage.
It was a valiant defense of the past, but progress is relentless. When C++17 came around a few years later, the committee voted to purge trigraphs completely. Not just deprecate them, but remove them entirely from the standard, despite IBM's continued protests.
Oh.
The era of the trigraph was officially over. Today, if you are a developer tasked with maintaining that ancient IBM legacy code, you have to run it through a dedicated translation script to parse the trigraphs into standard Unicode characters before the modern compiler will even look at it.
What an incredible technical journey. I mean, we started with the absolute constraints of 6-bit architecture where a programmer physically could not type an assignment arrow.
Yep.
We navigated the chaotic code-destroying bugs of the double question mark / preprocessor nightmare.
Yeah.
And we ended with a massive corporate standoff over backwards compatibility in the modern era of global finance.
Oh, quite a story.
It really reinforces the idea that the slick, invisible architecture of our modern digital world is heavily built on the crumbling foundations of old hardware limitations.
It does. It forces a profound shift in how you view the tools you interact with every day. Trigraphs finally died because our physical hardware, our keyboards, and our internal encodings caught up to our software ambitions.
Right.
But the cycle of technological limitation and workaround never truly ends. It merely shifts to a new domain.
Which brings up a fascinating thought to leave you with. If software had to bend over backward to accommodate the limitations of physical plastic keyboards in the 1970s, what happens to our code when we abandon keyboards entirely?
Oh, that's a great question.
Right. As we rapidly move toward voice coding, spatial computing, and AI-prompted software generation, physical keys are becoming less and less relevant. Will the specific Unicode symbols we fought so hard to standardize, the curly brackets and semicolons, suddenly become the obsolete trigraphs of the AI era?
It's very possible.
Are we just leaving a new set of archaic, invisible rules for the next generation of developers to unravel? It is certainly something to ponder the next time you tap that square bracket key. Thank you for joining us on this deep dive. Keep questioning the code.